Okay, this is the second part of shear force and bending moment example problem number 6. In the first part of the problem, we solved for the reaction forces of 5 kips at A, 12.88 kips at C, and 4.125 kips at E. In this part of the problem, the second part, we're going to go ahead and complete the shear force and the bending moment diagrams for the beam. So let's go ahead and shift over to OneNote where I'll do my work, and we'll get started. All right, so the first thing that we'll do is we'll recognize that we're going to work from left to right. We always work from left to right, never work from right to left. And one of the first things I'll do here is I'll go ahead and sketch in some construction lines. It works out that these lines are pretty much on top of the grids anyway, so that works out nicely. But just to make sure that we can draw with a bit more precision, I'll go ahead and sketch these in like so. All right, I might need to extend those a little bit as we go along. But so we're going to start off from the left end of the beam. And we start off at that point with a shear force equal to 0. As we moved from left to right, so I would say that V sub A minus is equal to 0. The shear force just to the left of point A is equal to 0. So the shear force just to the right of point A is equal to the shear force just to the left of point A plus the change in shear that occurs at point A. And at point A, we have a concentrated load acting up with a magnitude of 5 kips. So the shear force just to the right of point A has to be equal to 5 kips. So I'll go ahead and take, let's see, I'll take this as 5 kips. And I'll go ahead and sketch that in. And there we go. Okay, now I could say that the shear force just to the left of point B is equal to the shear force just to the right of point A plus the change in shear that occurs between points A and B. So this is equal to 5 kips, and the change in shear force that occurs between points A and B is equal to the area under the load diagram. So it's equal to that area. That is delta VAB, the change in shear between points A and B. So the area of that rectangle is equal to minus 1 kip per foot, and it has a length of 10 feet. So that means that the shear just to the left of point B is equal to a minus 5 kips. So using a scale of 2 blocks equals 5 kips, and that takes us there. Now, if we're integrating a 0th order curve, the load curve, then we get a first order curve for shear. So this is a constant here. So that means that this is a first order curve here, straight line. Now, a couple of things. This is a negative sign here on the minus 1 kip per foot because it points downwards. So that's true. The second thing is that the slope of this line is equal to the magnitude of load. So this is equal to a minus 1 kip per foot. So that means that the slope of that line is equal to a minus 1. All right, let me erase those for sake of clarity. There we go. Okay. Then you'll also remember, or hopefully, that when we did the reactions for this problem, we solved for the shear at point B and using a free body diagram, and we got a value of minus 5. So that works out to be true. That's good. Okay. Now, nothing happens at point B. Nothing happens between points B and C, actually. So what that means is that there's no change in shear until we get over to left of the point C, the left of that reaction force. So we could say that VC minus is equal to VB minus plus 0, no change. So that's equal to minus 5 kips. And I should label this. This should be 5. This should be minus 5, like that. Now, the change in shear at C, so let's see, the shear to the right of point C is equal to the shear to the left of point C plus the change in shear at point C. So this is equal to a minus 5 kips plus 12.88 kips. So that means that just to the right of point C, we have a shear of 7.88. I'll cheat a little bit. I know that it's 7.875, like that. So that's 5, that's 2.5, 5. That would be 7.5. So we're right about there. So 7.875. Okay, that's an instantaneous change in shear. Goes like that. Okay, nothing happens on the beam between points C and D, so there's no change in shear between points C and D. So shear force diagram looks like that. Okay, so what we can say is that the shear just to the left of point D is equal to the shear just to the right of point C plus 0, so that's equal to 7.875 kips. Okay, now the change in shear at D, so we say V sub D plus the shear just to the right of point D is equal to the shear just to the left of point D plus the change in shear at point D. So that's equal to 7.875 plus, and then this is a minus 12 kips, and it's negative because the 12 kip load at D points downwards. And then finally, that's equal to minus 4.125 kips. So that puts us right about there, and I'll sketch that line in like such. So minus 4.125 kips. And then nothing happens on the beam, no loads between points D and E. So there's no change in shear between points D and E. Then we could say that V sub E minus is equal to V sub D plus 0. So that's equal to minus 4.125. Then we could say that the shear just to the right of point E was equal to the shear just to the left of point E plus the change in shear at point E. So that's equal to minus 4.125 plus this concentrated load, 4.125, positive because it acts up, and then that takes us back to 0. So then we could sketch in this line here, and the shear force diagram closes, and that is a good sign. We could probably tell by observation that this point of 0 shear occurs at a distance of 5 feet to the right of point A. But in case we don't know that, we can prove that. I can show you exactly how to solve for it more precisely. Let's let that be the distance x to some point. We'll just call it I, not to infer that it's an inflection point. It's not. It's a point of 0 shear. But what we can say is that the shear at point I is equal to the shear just to the right of point A plus the change in shear between points A and I. So the shear just to the right of point A is 5 kips, and the change in shear between point A and point I is equal to minus 1 kip per foot acting over some distance x, and we know that that shear should be equal to 0. So scroll down just a bit, we can solve here, and we could find that x is equal to 5 feet exactly. Okay, now in case we didn't know that by observation, we can solve for it more precisely. All right, now let me go ahead and erase that. And all right, so let me scroll down here. We'll get to work on our bending moment diagram. Okay, let's get to work on the bending moment diagram now. And I've taken a second and drawn in the green construction lines while I had the recording paused. So we're going to start off the left end of the beam, work from left to right. So the bending moment just to the left of point A is equal to 0. In fact, the bending moment at point A is also equal to 0. Let's just go ahead and start with that. We know that the bending moment at a pinned end is equal to 0. So I'm going to go in and I'm going to call this point here. I called it point I just a minute ago, so I'll continue with that. We can say that the bending moment at point I is equal to the bending moment at point A plus the change in moment between points A and I. So that's equal to 0 plus the change in moment is going to be equal to the area under the shear force diagram between those 2 points. So that area is going to be 1/2 the base times the height. The height is 5 kips. The base is 5 feet. So that means that the bending moment at point I is equal to 12.5 kip feet. Now, I know that the slope of the bending moment diagram is equal to the magnitude of shear. So here at point A, I have a slope of 5. Here at point I have a slope of 0. So what I'm going to do, sketch that in there. So a slope of 5 at point A, slope of 0 at point I. I'm integrating a first order curve, so I know I'm going to get a second order curve for bending moment. I'm going to get a parabola, and it has to fit in there. So I know that that curve has to look like this. 0 slope there, and a positive slope at point A. So we go back over here now, and I can say that the moment at point B is equal to the moment at point I plus the change in moment between I and B. So this is equal to 12.5 kip feet plus 1/2 the base times the height. So the area is this area now. The change in moment is equal to the area under the shear force diagram. So this here was delta MAI. This is delta MIB, like that. So this is equal to minus 5 kips now for the height. This is equal to 5 feet for the base, and that's equal to 0. So our bending moment diagram has to get back to 0. At point B, I have a slope that is equal to -5, so I know that the slope of the bending moment diagram there has to be like that. At point I, the slope is equal to 0, so I know I need to fit a bending moment diagram that is second order. It's second order because the shear force diagram is first order, and it has to fit in there. And it should look something like that. There we go. All right. Now I could say that the bending moment diagram at point C is equal to the bending moment at point B plus the change in moment between B and C. So that's equal to 0 plus, and then the change in moment is equal to the area under the shear force diagram. So it's equal to this area here. So that's delta MBC. And that base is, well, base times the height. So height is minus 5 kips. The base is equal to 6 feet. So that means that when we get to point C, the bending moment should be equal to a minus 30 kip feet. So let's go ahead and sketch that in here. That's going to be down to that point. Okay, so sketch in here like that, and you can see this curve is actually continuous and it's smooth. There's no kink there because the slope just to the left of point B has to be equal to the slope just to the right of point B. So to go back in and fill in, this was 12.5 kip feet, and this is minus 30 kip feet right there. Okay. Okay, now I need to figure out the moment at point D. So I could say that the moment at point D is equal to the moment at point C plus the change in moment between C and D. So the moment at C is equal to a minus 30 kips, and the change in moment between C and D is equal to the area under the shear force diagram. So it's equal to this area here. So that's the change in moment between points C and D. Okay. So that's equal to a base dimension, which is 8 feet, and the height of that is 7.875 kips. So that means that the bending moment at point D is equal to 33.0 kip feet. So we go over here, 1, 2, 3 and a bit, and that would be the bending moment at that point. I'll use my straight edge again, and we get a linear bending moment diagram. We're integrating a constant curve up here to get a linear curve there. Okay, and then finally we could say that the bending moment at point E is equal to the bending moment at point D plus the change in moment between D and E. So this is equal to 33 kip feet plus the change in moment is equal to minus 4.125 kips, acting over a length of 8 feet. So that is this area here. So that is the change in moment between points D and E. So then if we do the math on that, that works out to be 0 kip feet. So this comes down here like such, and we go back to 0. Okay, now there is one last thing to take care of. This is an inflection point here. That's a point where the moment is 0. That's where the curvature goes from being positive over here on, negative over here to the left of that point to being positive to the right. So that is an inflection point. So we need to solve for the location of that in order to be complete. So that is going to be at this point right there. I'll call that X, and we'll measure it relative to point C. So what we can say is that the moment at the inflection point is equal to the moment at point C plus the change in moment between point C and the inflection point. So this is going to be equal to, the moment at C is a minus 30 kip feet, and the change in moment between C and the inflection point is going to be equal to 7.875 kips by some distance X. And that is going to be this area up here. So that is the area right there, delta MCIP. So if we do that, then what we find is that X is equal to 3.81 feet. So the inflection point lies 3.81 feet to the right of point C. All right, and if we were to go back and look at this thing drawn a little bit more carefully, then the shear force and bending moment diagram, it would look like that. Okay, is that when we solve for the reactions to this beam, we replaced the uniform load on segment AB with an equivalent concentrated force equal to 10 kips. And that's fine when we do the external reactions, when we're solving for the external reactions. In fact, it's not just fine. We don't really have a choice. That's really the only way to do that. But when we go and draw our shear force and free body diagrams, we can't use that equivalent external or that equivalent concentrated force. We have to use the, in fact, we have to use the actual distributed load of 1 kip per foot. So I want to make sure that I mention that, because if you use the equivalent concentrated force of 10 kips here for the represent the distributed load on segment AB, you get a different shear force diagram, you'll get a different bending moment diagram, and it's not conservative, it's not unconservative, it's just wrong. All right, great. Hope this helps.